Okay, so here we are in Chapter 13, Nonparametric Tests. So to recap, we've covered quite a bit of statistics thus far in the semester, and all the stats that we've covered have nonparametric equivalents. Talk a little bit more about this. Nonparametric tests do not require that the samples come from populations that have normal distributions or any particular distribution. I covered a lot of the reasons that we do nonparametric statistics in Chapter 11, but there is a disadvantage that I want to make sure that you understand. When we create categories from continuous data, we lose information. For example, if we ask in a survey how many years of experience in the lab somebody has, and we give them a choice of 1 to 5 years, 6 to 10 years, we lose a lot of information. There is a marked difference between 1 year of experience and 5, but if we make that a categorical variable and they check 1 to 5, we don't know whether they're 2 years of experience or 5 years of experience or 2 months of experience. So if you can avoid going from continuous data to categorical data, then definitely avoid it. But if it can't be avoided, it's okay to do. But note that you will lose information. Okay, so the way nonparametric statistics work is rather than use scores and means, they use ranks and medians. Take a look at the steps on pages 576 to 577 in your textbook, and it's very complicated. I took a whole semester on nonparametric stats where we did it all by hand, which was a bit silly because you're not going to ever do that. So we're going to use software. So there's a thing called the efficiency rating, and what this means here, we have the sign test or the WILCOXON signed rank test, right? 0.63 or 0.95. The efficiency rating means that it would take a sample size of 63 for a parametric test, would take 100 for the sign test, or for 95 for a WILCOXON test. So when given the option, you want to go with the parametric test because it's a more robust and stronger test than these nonparametrics. But if you can't, then they're definitely there for you to use. So like I said, the book goes into a lot about how to hand calculate. We don't need to do that. Since you already, and the good thing about this chapter is that it's nothing new. Since you already know the parametric version, I'm just going to show you how to do these nonparametric equivalents and how to do them in SPSS. The first test they talk about in the book is a sign test. I have never ever seen this used in research, and its efficiency rating is only 0.63, and so we're just going to skip it. It's silly. So we'll just use the WILCOXON signed rank test. Alright, so this is a test called the WILCOXON signed rank test for matched pairs. It's the equivalent of the paired samples t-test. It uses ranks for these applications to test a claim that the population of matched pairs have differences with a median equal to 0, or testing a claim that a single population of individual values has a median equal to some claimed value. So the requirements are that the data are a simple random sample, and it says run a histogram. The data don't need to be normal, but should be sort of a mirror image. We're going to get this from the output in SPSS. We're not going to have to do that part. All right, so looking at the example on page 577, freshman 15, the claim that when you go off to college, you gain 15 pounds. We want to know, is it true? So the null is that there is no difference in the beginning and ending weights for a group of individuals from September to April. And the alternative hypothesis is that there is a difference. So here we have the September weight, April weight. They've got this is how you would calculate it if you were going to do it for by hand, but we're just going to let the computer do it for us. So I entered this top row for the September weight and then this second row for the April weight. And then we're going to go to Analyze, Nonparametric, Related Samples. So here we have Analyze, Nonparametric, Related. We're going to leave it at Automatically Compare Observed Data to Hypothesized, this top one. And we're going to click Fields, which will take us to this. Well, when you do that, so between this step and clicking the first step, you may see this dialog box when you first open it. It says Measurement level, proper measurement level is important for this procedure. It's unknown for one more field in your data set, blah, blah, blah. Just hit client scan data and then you'll come to this. And it says, so the first thing we're going to click is fields. All right, so when we click fields, we'll have both of our variables here. And we're just going to bring September over and April over. Okay? And it says, we're going to say choose customize test, which is right here. So we click settings. So it's kind of hard to do it, you know, step by step. So the first one is fields, which gives us the variables. And then we'll go back and we'll click settings, which then brings us here to customize test. Okay, and then we're going to choose WILCOXON matched pair signed rank two samples, and then we'll click run. Okay, so when we get our output, we can see that our null hypothesis is that the median of differences between September weight and April weight equals 0, and we can see that we reject because it gives us the decision for us. We reject the null hypothesis and our p-value is here. Here's our sample size 10. Here's the test statistic and the standard error. Here is the standardized test statistic that we are going to report and our p-value. Now when I said that histogram, we wanted to see it be somewhat symmetrical. The book says the population of differences has a distribution that is approximately symmetric. Well, I wouldn't call that, I mean, maybe approximate. And then we get the distribution of our continuous field and our continuous field for the pre-test and then for the post-test, okay? And you can see that we have a mean of 64.3 and then a mean weight of 66.6, and those are in kilograms. All right, so then we're going to report it. So I just made a recopy of this particular bit of this slide. So we report our results. You can see from the previous slides the two histograms on the right, these ones I showed you here, 64.3, 66.6, that the mean score for September is 64.3 kilograms and for April is 66.6 kilograms. Evaluating the output above, there is a significant difference with the freshmen showing moderate weight gain. So you would say there was a statistically significant increase in weight gain from September to April. Z is equal to 2.09, P is equal to 0.03. All right, so now we're going to look at the Mann-Whitney U, and I have a slash here, WILCOXON rank sum. They are the same test. These are equivalent tests, and everybody calls it the Mann-Whitney U. It's referred to that more commonly. So that's what we're going to use because that's what SPSS calls it as well. It's the non-parametric equivalent of the independent samples t-test. So the null is that two independent samples come from populations with equal medians, and the alternative is that they don't. So we can have a one-sided that median 1 is greater than median 2, median 1 is less than median 2, or non-directional, median 1 is not equal to median 2. We're just going to go like with all of them, we're just going to use the non-directional, but you can just know that the book is denotes this, and that's always a possibility to say one is larger than the other. All right, so we're going to look at pulse rates of males and females. Works just like an independent samples t-test. You enter the data the same way, so here it is in table 13.4 on page 583. You've got males' pulse rates and females' pulse rates. We've got 11 females and 12 males, right? So I went through and I coded boys as 1, girls as 2, and then I loaded in their pulse rates. It did this measure scan thing again for a new data set, so I just want to remind you that if you see that, don't freak out, just say scan data. All right, so it works just like an independent samples t-test. You enter the data the same way with, you know, a grouping variable for your categorical variable, and then the continuous variable in another column. We're going to go to Analyze, Nonparametric, Independent Samples. The null is that the pulse rates are the same. The alternate is that they're not the same. So it's the same thing. You go Fields, you bring pulse rate over, and now we've got grouping variables, so we have to bring gender over here. Then we're going to click Settings. Here we are in Settings. We're going to customize, and we're going to select Mann-Whitney. Then we're just going to click Run. All right, so then we get our output, right? And here we are, the independent samples Mann-Whitney U test summary. We have 23 in our data set. We get all these different test statistics, but we're going to use this standardized one. This is our Z-score. And we're going to use, it doesn't matter which one we use, we'll use the exact p-value. All right, so the conclusion is that there is not sufficient evidence to reject the null hypothesis. Pulse rates are the same across genders. Z is equal to 1.27, P is equal to 0.21. This graph is something that SPSS gives us we didn't ask for. It's called a population pyramid, and it's used to evaluate whether the two groups have similar distributions. Looking at this, I would say they do not. But it doesn't matter because it wasn't SIG. And then here's our histogram for the continuous variable, and then just the bar chart for our categorical variable. All right, so now we're looking at the Kruskal-Wallis H-test for 3 or more samples. This is the non-parametric equivalent to the one-way ANOVA. Remember that the only way ANOVA is different, well, they use an F-test, but the way it's different is that now our independent variable has 3 or more categories. So we have low, medium, and high. So on page 590 in the book, this is from a data set we've talked about before. It's the IQ scores for children who have low, medium, and high levels of lead exposure. But we're using a little subset, so we've got 5 scores, 6 scores, and 5 scores. So I went through and coded them 1, 2, and 3, loaded in the continuous variable, and we do the same thing like we did before. We would pull up non-parametric. I'm not showing it to you each time because it's the same thing over and over again. Non-parametric, go to Analyze, non-parametric, slide over independent samples. Now we're here, we would choose fields, we'd move over the continuous variable, we'd move over the grouping variable, then we would click Settings and click Customized Tests, and you'll see this in the homework video as well. You click Kruskal-Wallis one-way ANOVA, and it automatically populates this all pairwise. We're just going to leave that alone. That's like a post hoc test. Remember the LSD, least significant difference test? That's what that is. So we do that, and we click Run. And our hypothesis is that the distribution of IQ scores is the same across categories of lead level. And we retain the null hypothesis. We say that they are the same. And it tells us it ran an independent samples, an independent samples Kruskal-Wallis test. And here are our test statistics. It gives us a box plot. And so we'd say 16 individuals in our data set, the test statistic, and it's got this little tiny A and B, and it says it's adjusted for ties, and multiple comparisons are not performed because the overall test does not show significance. So unlike the one-way ANOVA, if you ask for multiple comparisons, they give it to you regardless. Here, if it's not significant, you don't get them because we have a p-value of 0.77. So I would write it up. A Kruskal-Wallis H-test was run to determine if there were differences in IQ score between 3 groups of children with differing exposures to lead, low, medium, and high. Distributions of IQ scores were similar for all groups, as assessed by visual inspection of a box plot. Median IQ scores were not significantly different between groups. And now this is no longer a z-score, this is a chi-square. So we say chi-square with 2 degrees of freedom is equal to 0.517, p is equal to 0.772. And I don't have the sample size in here, I just did it like that, and that's fine. All right, so let's do one that is significant. And I got this from the back of the book. I had to download the entire data set. So we've seen this one as well. We want to look at the level of cotinine in smokers, non-smokers, and those non-smokers who are exposed to smoke, and see if they have the same level of cotinine in their blood. So alternative hypothesis is that the null is that they're the same. The alternative is at least one is significantly different. So we same old deal. We go Analyze, non-parametric, independent samples, choose your fields, move them over. Cotinine comes over, grouping variable goes over. Then we come up here, we click Settings. This becomes highlighted. We click Customize Test, and we click Kruskal-Wallis. Same thing we just did. Then we hit Run. And now, all right. So now this slide is a bit busy, and I apologize for that. But I just didn't want to have so many slides. Death by PowerPoint. Okay. So the null hypothesis is that the distribution of cotinine is the same across levels of smoke level, and we reject the null hypothesis. We have a highly significant finding. Here's our sample size, here's our test statistic, degrees of freedom, and our p-value. We get this without asking for it. It gives us a box plot. It gives us the multiple comparisons, so we have no contact smoke to contact smoke, no contact smoke to smoker, and contact smoke to smoker. And each of these is highly significant. And it gives us this kind of groovy looking triangle that we don't really need to do anything with. It's just showing you the different spokes of these particular comparisons. So no contact smoke to smoker, that's this one. No contact smoke, no, this one. No contact smoke to smoker, that's this spoke of the triangle. We have no contact smoke to contact smoke, that's this top one, and then here to here. And you can see that we reject an all. There are differences in the level of coat-9 by contact. So chi-squared degrees of freedom 2 is equal to 62.3 right here. P is less than 0.01, and the pairwise comparisons between each group are significant. Okay, one last one to do. Spearman's row, which is rank correlation. Spearman rank order correlation, often abbreviated Spearman's correlation, calculates a coefficient R sub S. That's showing you that we're talking about Spearman's row, not Pearson's R, or the Greek letter R, rho, which is a measure of the strength and direction of the association between either two continuous variables, two ordinal variables, or one ordinal and one continuous variable. Okay, so we're going to look at time spent watching TV versus cholesterol level for men aged 45 to 65 years old. We can see there's a little bit of a curve here, but there is a positive correlation. And it's so simple, I'm not even going to go into it at any length because it's the same thing you do. You go, I did a scatter plot just to see the association. I went to graphs, legacy dialogue, scatter dot, and moved the variables into the X and Y and clicked OK. That's what gave me this scatter plot. Then I just go to analyze correlation bivariate, and this will be checked, this Pearson, but we just uncheck that and check Spearman, and just leave everything else OK. Click OK, and we can see that there was a statistically significant strong positive correlation between daily time spent watching TV and cholesterol concentration in males aged 45 to 65 years old. R sub S, this is Spearman's row, 98, that's the sample size, so you have to remember to take away 2, it's the same thing, the degrees of freedom. So 100 minus 2 is 98, is our degrees of freedom is equal to 0.729, P is less than 0.01.